Hello, I'm Bill Craig from Avid Systems in Mount Airy, Maryland. Today we are going to unbox the AVS-4000 software-defined radio. In this video we'll cover 4 topics. The first topic is what's included with your AVS-4000. The second is to quickly go through the user's manual. The third is software installation. And the fourth is to show how to quickly get to a GNU Radio demo with your AVS-4000. So let's get started. Your AVS-4000 ships in a box like this. There are 3 different items in the box. One is the AVS-4000 SDR. Then there's a USB 3.0 Type A to Type C cable and an SMA loopback cable. Let's open up the AVS-4000 first. Okay, so here's the AVS-4000. It's built in a rugged aluminum chassis. Here's the front panel. You can see there are 2 SMA connectors on the front panel. One is a dual-purpose RX-TX SMA. That's used for TDD operation. And then there's a separate TX-only SMA connector. The 2 then can be used in FDD mode. Notice the 2 indicator lights down below, the 2 holes below the SMA connectors, I1 and I2. They're LED lights that we'll discuss those functions in a couple minutes. On the back panel, there are 3 RF connections, one for a GPS antenna, the other for a 10 megahertz external reference, the other for an external 1 PPS. Next to it's a USB-C connector that's used for data transport, command, and control. Then there's an auxiliary power port. It's also a USB Type-C connector. And it's used for users that don't want to power the AVS-4000 off of a USB port, or they have other power rails such as a 9-volt or 12-volt rail that they wish to power the AVS-4000 off of. There are 3 indicator lights across the bottom, I3, I4, and I5. We'll go through what they mean later. Notice that there's an access panel door on the side of the AVS-4000. When that panel is removed, it gives you access to a connector on the AVS-4000 printed circuit board that provides GPIO control for external circuitry. Here's our cables. So an SMA loopback connector and our USB connector. Okay, so that's what's included in the AVS-4000 box. So let's quickly go through the manual. Okay, so the AVS-4000 user manual starts off with some introduction, goes through system specifications, then provides a block diagram of the printed circuit board. This block up here is the RX path. This is the TX path. The RX and TX paths are both broken up into 2 paths. The main path, which has a 5 filter bank in it, and the frequency extension path. This path extends the frequency range of the AVS-4000 down to 2 megahertz. There is a selectable SAW filter on the output of the low band frequency extension. One is a 50 meg SAW filter, the other is a 10 megahertz SAW filter. There's a switch at the input of the RX and at the output of the TX. This allows the TX to be switched to the dual purpose SMA. Alternatively, it can be switched to the TX only path. The TX path has a 15 dB amplifier that the user can select to turn on. Obviously, this will provide additional power for the TX signal. The amplifier is also followed by a 5-stage filter bank, and then again the switch that allows it to switch to the RX-TX or TX only path. The AVS-4000 is built around the analog devices AD9364 and the Xilinx Artix 100T FPGA and a USB 3.0 controller. A TCXO is used as the system clock. It runs both the FPGA and the 9364, and it is the source of timing for the AVS-4000. The TCXO can be trained by the internal GPS module, the external 1 PPS, or it can be phase locked to the external 10 MHz using a hardware PLL. The manual next covers all the external interfaces. Here's the two SMA connectors we saw on the front panel when we unwrapped the AVS-4000, and here are the two indicator LEDs below that. So indicator 1 is a green LED, and it indicates that the RX path is active. Indicator 2 is a yellow LED, and it indicates that the TX path is active. Here's the rear panel, GPS, 10 MHz, and 1 PPS input, two USB connectors. And here are the three indicators in the rear panel. Indicator 3 is a yellow LED, and it indicates that the selected PPS is active. This yellow LED will blink at a 1 PPS rate. Indicator 4 is a blue LED, and it indicates that the system is powered. Indicator 5 is a green LED. It indicates that the selected reference mode is in a locked condition. Here's the door on the edge of the AVS-4000 chassis. A connector can be exposed by removing this door. There are general purpose I/O connections on this connector that can be programmed by the user to control external circuits like TR switches. This table shows where the GPIO are connected on that connector and what voltage rail they're associated with. Avid Systems does sell an optional breakout board for that GPIO connector for users that want to experiment or use that GPIO. Reference and time-based option settings are described in the manual as well. It shows the user how to set up each of the different time bases for the system. The time can be based on the GPS module, an external 1 PPS, an external 10 MHz, or a combination of the 1 PPS and 10 MHz. The manual provides further details on the RF, on the RX and TX paths. Then the manual discusses the digital signal processing paths that are in the FPGA. The FPGA contains a single digital down converter path and a single digital up converter path. The digital down converter path provides filtering, tuning, and gain to the RX signal that comes from the 9364. The digital down conversion path is capable of decimating by 8192. The digital up conversion path is responsible for interpolation, tuning, and gain of the TX signal bound for the 9364. The digital up converter can interpolate up to 8192. Next is the VDA49 packet. This picture describes all the VDA49 fields that are currently implemented in the AVS-4000. These tables below describe all the fields in the VDA49 packet. And then there's a mechanical drawing of the AVS-4000 for users who wish to install the AVS-4000 into their own system. Next are detailed instructions on software installation. So we'll go ahead and install the software on the AVS-4000. Okay, so before we get started with the AVS-4000 installation, you should update your system's operating system. Okay, so now that the operating system is updated, we're ready to install the AVS-4000 software. The software for the AVS-4000 is made available to users through a software repo that's maintained by Avid Systems. In order for your system to securely download the software for the AVS-4000, you must first get an authentication key from the Avid repo. The packages from the Avid Systems repo are all digitally signed. So you'll need to copy this line to add the authentication keys to your system. Okay. Next, we need to add the Avid Systems repo to your system sources list. I'm going to have to do 2 copies here because this command is on 2 lines in the manual. Okay. Now we'll go ahead and update the package list. Then we can update the packages. Now we can install the AVS-4000 daemon and GNU Radio components. So let's go ahead and do that. Answer yes. Okay, now that that's finished, the installation, during the installation there are some USB UDEV rules that were loaded down to the system. We need to copy those UDEV rules to your system's UDEV rules.d file. That will allow the AVS-4000 to have access to the USB port. And we can activate those UDEV rules. Okay, so the AVS-4000 software is now loaded. The manual does talk about if you aren't able to have access to the Avid Systems repository, we can get you the Debian packages that are needed for this on a separate media, whether it's DVD or a flash drive or whatever. Okay, so the system's now ready to go. The AVS-4000 daemon is installed. One of the things that's necessary for you to know is that you don't want to run the AVS-4000 daemon as root. There are configuration files that the daemon uses to map AVS-4000s to different USB ports. If you run the AVS-4000 daemon as root, it's going to cause some permission issues when you try and run it. Okay, let's explore where the software was installed. So the AVS-4000 daemon is installed in user bin. There it is. And we have, there's also some Python example scripts that were downloaded during installation. There's the example Python scripts. These scripts will provide you with examples of how to interact with the API that is exposed by the AVS-4000 daemon. The AVS-4000 daemon is a high data rate, lightweight, socket-based interface that uses JSON messaging for API access. And these Python scripts will show you and give you a feel for how that works and give you examples of how you interact with the daemon and the API. So the AVS-4000 daemon, when you initially launch it, it launches a device manager. The device manager handles detecting and identifying AVS-4000 devices. For each AVS-4000 device that the device manager finds, it launches an AVS-4000 device controller. You talk to the device manager and the device controller through TCP ports that start at 12,900 and then increment one up for every device that's found on your system, for every AVS-4000 that's found on your system. Okay. So that's how that works. There's an AVS-4000 device manager that controls all of the AVS-4000s that it finds each time it finds when it launches a device controller. So let's go back to the home directory here. And let's type AVS-4000 daemon. Okay, the help menu provides you with all the switches that are used for the AVS-4000 daemon. The -V produces a verbose output. The -D puts the daemon into an interactive mode that allows you to actually type commands into the AVS-4000 daemon. Then there's a variety of switches that control how the AVS-4000 is reset. This -N switch actually launches an AVS-4000 daemon in device control mode. So you actually have to specify which device you want to talk to, and it allows you to interact directly with a particular AVS-4000. This is used mostly for debug. So let's go ahead and launch the AVS-4000. Or first, before we do that, let's go ahead and install GNU Radio here, so that we are ready to roll with our demo. So first, we'll install GNU Radio. GNU Radio is already installed on this system. During installation, there was a GNU Radio companion flow graph that was installed in the shared doc examples directory. We need to copy that to the home directory. So I'm going to do that. Again, this is a command that spans 2 lines, so I'm going to do 2 copies here. Okay, that'll place that GNU Radio companion flow graph into the home directory. Okay. All right, so let's hook up our AVS-4000 now. So we're going to hook up the USB port first. See the blue LED indicator lights indicating that the system is powered. Then we're going to install our loopback cable. One side hooks to the TX SMA, the other to the RX SMA. Okay. Okay, so now let's launch the AVS-4000 daemon. And I'm going to launch it in verbose mode and interactive mode. We'll launch that. See, it found the device. It's booting it. Now it's programming it. What's going on here is the FPGA is being programmed, the USB 3.0 controller is being programmed, and we see that it has found the AVS-4000, has assigned it device number 4 is ready. So we type in, let's type in help here first. So here's a number of commands that you can type into the AVS-4000 daemon. There's a lot of commands here, there's a lot there. There's API commands that you can get help on. It shows all the API commands. I'm going to use the list command here first, and it lists device number 4. AVS-4000 was found at device number 4. So now we take a look at this, and we see that now not only is the blue light blinking, but we have a 1 PPS light, the indicator going. So this is blinking at 1 pulse per second, and so our timing source right now, because we have no external interfaces, is the internal TCXO just free running. That's our internal time source right now. Okay. So now we can now we can actually run our GNU Radio. We can launch GNU Radio Companion. This is done by going to the Activities section of Ubuntu and typing in GNU Radio. Select GNU Radio Companion. Then you can do File Open and select the AVS-4000 loopback example.grc. So this is the flow graph. Let's take a look at this flow graph for a second. Real important issue here. You have to make sure the device number matches the device number that was found by the AVS-4000 daemon. If you remember, I can go back to that. You'll see that it came up and found device number 4. So I need to make sure that device number 4 is in this parameter. That's important because if we remember, we talked about the AVS-4000 daemon is a socket-based daemon, and the device number and the port number of the socket are tied together. So if you don't have the right device number, you're going to get a failure to connect to the socket. So what's going on here in this flow graph? We have a signal source that outputs a 500K sine wave sampled at 10 megahertz. That goes into the AVS-4000 transmit block. It's then transmitted out of the TX port at 2.395 gigahertz. The receive port receives this at 2.395 gigahertz. The FPGA then decimates this signal down to 10 megahertz and transfers it to the host where we have a time sync and a frequency sync running. So let's go ahead and launch this. Now, one thing I will tell you is that this video editing software that I'm using has issues with the pop-up windows that GNU Radio creates. So I may have to come in here and place add another GNU Radio window into this. It's just kind of a weird thing that the video software does. Okay, so it has popped up on my screen, but it did not pop up here. So what you see is here is a status window for the AVS-4000. It displays things like the device number, the serial number, different temperatures on the board, the RX sample rate, TX sample rate, a variety of status conditions on the board. So I'm going to go ahead and add a window here to the video processing software so you can see what GNU Radio is actually doing. So okay, GNU Radio is actually displays this window alongside of the status window. What you see is a slider bar here to slide the TX transmit frequency, which is currently at 2.395 gigahertz. Same for the RX frequency. The digital up converter output gain is currently set to 0 dB. The digital up converter frequency is set to 0 hertz. The DDC, digital down converter output gain, is set to 0 dB. And the DDC frequency is set to 0 hertz. So what we see here is in time we see a sinusoid, and it is indeed the 500 kilohertz sinusoid that we set up in our GNU Radio flow graph. So to kind of play around with some of these parameters, the DDC output gain can be changed. You move that around, you can see the amplitude changing in the time domain. And you can also see it in the frequency domain as well. And we can actually tune out that 500,000 hertz sine wave by typing this into the DDC frequency of 500,000 hertz. And we see that takes it right down to DC. Okay, so let's take a look back at our AVS-4000, see what it's doing. So we see now that we've got the RX and TX are active. We see the two LEDs on the front panel are both active, saying that RX and TX are both active. And we still have the same 1 PPS and blue LED indicating that power is on the back panel. Here's our GNU Radio demo again. Some things you'll notice in the time domain, you'll see some black numbers flashing across there. They're actually time tags. So that's from the time stamping of the V249 packets are passed along to the GNU Radio as a time tag. So that's our demo of the AVS-4000 in GNU Radio. I hope you enjoyed this video. If you have any further questions, please don't hesitate to call at 301-703-8195 or drop us an email at info@avid-systems.com or check us out on the web at www.avid-systems.com. Thanks for attending this unboxing video. I had fun doing it, and I hope you have some interest in the AVS-4000. Please don't hesitate to give us a call. Have a great day, and thanks.